Now for a topic that I absolutely love. We're going to discuss the extrasolar planets, or exoplanets. Both terms are used very interchangeably. So, all the systems that we've described throughout this section is just a process of gravity and conservation of angular momentum forming protostars, stars, and the range of planets that we see, whether they're rocky or gas giants, depending on their temperature and masses. Well, there's nothing special or specifically unique about our solar system. So all these processes that we see here should be commonplace. We should expect that there are planets outside of the solar system. And to this day, we now know that there are thousands. Every year, this number keeps growing and growing. When I first started teaching this course, we were in the about 4,000, a little shy of it. Now we're almost at 5,000 extrasolar planets discovered now. This picture here is just a artist's rendition that every star throughout the cosmos probably has some number of planets orbiting around it. There will be 5 techniques that we'll discuss in this section that's used to find these extrasolar planets. And one thing I really want to emphasize here was that just a few weeks ago, I would have said only 4 techniques. So this is a ever-growing field of astronomy. We are always finding new and better ways to discover things, to learn more. So as a time reference, this is October 2019. Let's go through the exoplanets and how we find them. I've ranked these methods based on the number of exoplanets so far discovered by them. So the first one will be the transit method. And it's just based on this idea of a planet going between our view of the star and the star itself, causing this diminishing in the amount of light we see from the star. In essence, the area of the planet versus the area of the star, that ratio tells us how much the dip in light is going to be, how much the light's going to be blocked. And this is our primary method. We've gotten about 3,119 planets found this way. But think about an easy limitation. You need the planet to transit this way. If we look throughout the cosmos, any planets going around this direction around us won't intersect. It has to be this very specific type of crossing. But it is very effective. We see the star's brightness dips, and we get to find a planet. Some limitations of this method: well, what if the planet's really tiny and we can't distinguish between, say, just gas in our atmosphere versus gas out in the solar system? So this method works best for the biggest planets, the giant planets orbiting a star. Our next method is called the spectroscopic radial velocity, or just a radial velocity method. And this is all based off of Doppler shifts in the motion. Think back to our previous sections. We discussed about bodies orbiting around each other. And something like Jupiter and the Sun, it's not just Jupiter orbiting around the Sun, they orbit around their common center of mass. Well, look what happens to the star as it's orbiting around its common center of mass with its planets. Here the stars are going away from us. Here it's coming towards us. So there'll be this loop of blue shift as it approaches us, red shift as it goes away. Here on the animation we see our red shift. Now the star approaches, blue shift. So this planet is constantly Doppler shifted due to the orbit between itself and its common center of mass with the planet that's going around it. This method has been widely successful too. It's gotten us 764 planets so far. Once again, this is limited to massive planets. The more massive the planet is, and the closer it is to the star, the more likely, the more successful this method is going to be in discovering that planet. Going down our chain, this next method is called a gravitational microlensing. Now, before I show the animation, let's try and describe the setup of what's going on here. What we're looking at is a distant background star. Now, between our line of sight and that star will be another one that potentially has a planet orbiting around this. So this method will not find planets orbiting this star. It'll find planets orbiting around this star that's going across our view. Now, how does this work? Well, special relativity, general relativity tells us, or special and general relativity tells us that gravity is going to be distorted around massive objects, and the amount of distortion depends on how massive something is and where the mass is distributed. So as this star and its planets crosses our field of view, there's going to be what's called a microlensing effect. The light coming from this star will get focus, kind of like going through a lens. Now, this figure here is showing the difference between our line of sight of the star versus one of our satellites, Spitzer. And the point here is that this is a way for us to cross-reference. Spitzer will see a dipping, a focusing of that light, and then our ground-based telescopes will see it with a little bit of delay, and that's just due to the distance between Earth and Spitzer. So with that, let's actually go over to the animation and see how this works. So here's the distant background star, and it's radiating its rays of light. The grid here, that represents space-time. We're looking at basically a 2D representation of it. So this grid is where light travels out through. The star itself will distort space-time. That's why you see this kind of folding in of space-time due to just the presence of the mass there. Now, here's us on Earth, and we see our line of sight of this star. Now for the important part, the microlensing aspect. You'll have another star that has a planet attached with it, some planet orbiting. Relative between us and the background star, you can have this star and its planet moving. And you're seeing how it's creating this microlensing effect of the rays. Look at these rays, crossing, crossing, crossing. It's just due to these distortions in space-time because of the mass of this star and its corresponding planet. So this method has allowed us to measure whether this star had a planet riding along with it. So far, it's netted us 83 planets. So exciting. The fourth method we'll discuss is direct imaging. It seems obvious, but it's honestly not a very useful method because it's so difficult. We've only found 47 planets through this direct imaging method, and it's exactly what you think. Look at your telescopes, see a star, and try and find the accompanying planet. The problem is that the star is super bright compared to the planets. Any light coming off of the planet is just light that was reflected off of the star. So the star radiates light, that light will bounce off the planet and reflect towards us. So we have to do this correcting to block out the star's light and try and see the glow from its corresponding planets. Once again, this is our fourth tool in our bag now of finding our exoplanets. Our fifth and final technique we'll discuss in this section is called astrometry. Now, the concept has existed for a long time, but we only recently found a confirmed planet discovered this way. What you're looking at is the star with its planets relative to neighboring stars. So zoom back in. Here's the star with its planet orbiting around it. Remember, they'll have that wobble in its motion. So all we have to do is see that star's wobble compared to its neighboring stars. Well, the type of wobble will have based on its orbit with its accompanying planet. Well, let's tell us that this star's wobble relative to its neighboring stars will predict the mass and distance of a planet orbiting this star here. Now, summarizing our discoveries so far, most planets we have found have been objects that are 10 times Jupiter masses. These things have been gigantic and relatively close to their stars. So we started calling them hot Jupiters. Now, one key point to emphasize here is that these hot Jupiters do not perfectly match up with our nebular hypothesis. It's why we still refer to it as a hypothesis. Our nebular hypothesis doesn't correctly predict the location and mass of these hot Jupiters. It can explain some aspects of them, but not everything. Emphasis for now, for planets we've discovered, it's been mostly hot Jupiters. And that goes back to that wobble of the star around its accompanying planet. The more massive the planet is, the bigger the wobble on the corresponding star. And that's what makes these easier to find, which correspondingly means that most of the planetary systems we've found so far doesn't look like ours. That's not to say that our planetary system is uncommon. It just means that our techniques are not refined and precise enough to locate planets like ours yet easily. We are getting better and constantly finding new techniques. Of obvious interest to us is finding planets that exist inside the habitable zone, which is just the range of distances away from a host star that liquid water can exist. Looking at our own solar system here, Sun, Mercury, too close, it'll be too warm, no liquid water can be sustained there. Venus is on the outer edges of this potential habitable zone where water can condense down into a liquid. Earth, obviously, we have our wonderful liquid water. Mars turns out to still be in that habitable zone of our sun too. We do suspect there is liquid water on Mars. We definitely know there is definitely water on Mars too. Now, the Kepler mission, that refers to Kepler's satellite, and this has been one of our primary sources for finding exoplanets. One of its planets that it discovered that's of particular interest to us is a star, or in its system, Kepler-22, and its planet, Kepler-22b. Yeah, we don't always have creative naming conventions. But what we know about Kepler-22b is that it lives in the habitable zone around its host star. Once again, that range of space where liquid water could potentially exist. And one last thing to emphasize here, what the habitable zone is, it's not defined by just one distance. The size of the star, its how much power, how luminescent it is, will vary the potential range of habitable zones around a star. Here's that picture of different stars, and the green being their habitable zone. And so there'll be this wide range of potential options here. So for us to understand the habitable zone of a star, we need to know the size of the star, how luminous it is, and finally, if there's any planets around that star. We've only found a handful of planets that live in the habitable zone of the stars. And that is now a new question of, well, we found these planets, how do we find if there's actual water there? And there are a lot of great ideas out there, but the science is still being conducted. We're still doing our investigations. We'll keep hearing exciting news. Most recently, we had a planet with water that we think is in its atmosphere. So we're getting closer and closer. And one day, I'm very convinced we will find planets, exoplanets, with water on them. So there's a figure summarizing the bands of planets that we have found out there. Hot Jupiters being the most. We'll have these tiny orbital periods. Look at this. A planet that's more massive than Jupiter having a period around its star on the order of 10 days. Yeah, the hot Jupiters are crazy and amazing. On this scale, you'll see the relative size of these things. Keep going around these other objects we found. Cold gas giants. Hoping for a lot of potential ocean worlds and ice giants. Not certain yet. Lots of potential rocky planets and lava worlds. And this frontier, these are going to be the smallest, slowest moving planets out there. And we just need to refine our techniques to find them. And that's where future research is going to focus too. Wrapping up everything we discussed in these sections, we start off with the nebular hypothesis. Take a giant gas cloud and let it condense down, and because of the conservation of angular momentum, how it goes from a sphere to a rotating disk where the planets will aggregate. Protostar and star in the middle, planets, accretion, growing by accretion around that. We discuss 5 techniques for discovery of exoplanets, and one emphasis here is that the number of exoplanets and the methods we use to find them keeps growing every year. And to conclude, here's a picture of Jupiter with exoplanet TRES-3b, which is an example of a hot Jupiter. All right, with that, we'll call it into this section, and I'll see everyone next time.